What up, everyone? How'd you get into computer science inspiration? So I was going to college for electrical engineering, and I hated it. I liked it in the beginning when we were like building circuits, but electrical engineering EE gets to a point where you're just doing all kinds of crazy math that kind of gets disconnected from reality. So I dropped out of college. And when I reflected on things, I obviously ended up coming back. But when I reflected on things, the courses I really enjoyed in EE were the programming classes. There are a few of them, but I really enjoyed those so much. So I'm like, well, let's give computer science a try. And then it of course worked out for me. And I absolutely loved it. The big thing I like about computer science is you're sitting in a class, you're learning things, and then you can just immediately apply those things to your own project and just see it all in action, just right away, immediately applicable. With EE, which is of course the big one that I have to compare to, and business, I guess. With EE, if you want to take what you're learning in class and apply it to your own project, you got to spend a lot of money. You got to buy the hardware. You got to build the a whole thing. It's not immediately applicable, even if you're just waiting for the parts to come in. Like you can't just apply it. But computer science, I learned about inheritance. I got a side project. I'm like, oh, that that could apply right here. Why don't I use inheritance here? And just the immediacy of it. The whole idea that I could learn something and just build something cool and go use it very, very much appealed to me. And we don't have many courses where you just learn about random bullshit. So that's nice too. Where at least EE did have that. That technically applied, but nobody cared. And arguably, people say that about computer science too. How much do you have to know about the operating system internals? So there are fair counterpoints to that. But for me, CS is where it's at. All right, so let's get started. Today we're learning about trees, so programming test 5. And let's just jump into it. I want to go through this content. I have a few tree examples that I want to show, but not too much that I really need to show in the code. I want to write some, do a little live coding, maybe not much live coding, but at least running the debugger and getting another example of that. So we have some time to hopefully slow down the pace a little bit with these slides and then talk about programming test 5 after we see the content that's being assessed on programming test 5. So let's just jump into some slides here. And then it's going to take me 6 weeks to hit the right button there. I guess I did the right one, but I almost did the wrong one. All right, binary trees and traversals. So today we're learning about a binary tree, but binary trees in general. So what is a binary tree is actually pretty simple, pretty straightforward at one level, and then of course we'll take the whole lecture to explain all the implications of that, how to work with them and stuff. But the structure, it's like a linked list. It's a node-based data structure, but instead of having a reference to another node like a linked list does, a binary tree node has a reference to 2 other nodes. So now instead of just one reference, it's 2 references. Everything else is the same structure as a linked list. So a binary tree node has the value that's stored at that node, and then references to 2 other nodes. And a binary tree in memory really is just a reference to the first node in a binary tree, which we call the root node of the tree. Where the first node in the linked list was called the head of the list. This is the root of the tree. So the tree is kind of upside down. The root is going to be at the top of the tree, and then the branches go down. But computer science is upside down like that sometimes. A little bit of vocab. The references are going to be the left and right references, usually called the child nodes. So if I say the left child or the right child, that's similar to the next node in a linked list, but we have to have some word to differentiate the two nodes. So left and right. And from those nodes' point of view, the node referring to them is going to be its parent node. And if you get into trees, like in future classes, we'll suffice with really just child nodes. I won't really talk about parent nodes much at all, but we'll suffice with just child nodes. But in other courses where you learn more about binary trees, this analogy extends throughout the whole family tree nomenclature of grandparent nodes, grandchild nodes, aunt nodes, uncle nodes. All of that applies. Descendant nodes, all that terminology will apply. We really, in CS, we like the family tree analogy, and then also the physical tree, the natural tree analogy. We have branches, leaves, root, we already saw. So there's kind of two simultaneous analogies that run through these that a lot of the vocab stems from. But child node, that's going to be the big one that we'll use left child, right child. And root node. So here's an example, a visualization of a binary tree. So we have nodes, and we'll have some variable that I named root here that's going to store a reference to the root node of the tree. And then that node is going to have its value. So this is a binary tree node of integer, or binary tree of integers. It's going to have its value, and then two references, left and right. So the left reference is a reference to this node here. Its right reference, the right reference of the root, or the right child of the root, is this node here with the value 8. And then each node can have a left and a right child, left and right references. So we have this kind of branching structure to our tree, whereas a linked list was a linear data structure. This is our first non-linear data structure. We have multiple paths, multiple choices to be able to take to navigate through this tree. And just like a linked list, the references can be null. So left and right are null. If we reach a node where left and right are both null, that is technically what we call a leaf node, but I won't get bogged down on that terminology, not in 116 at least. This is a node that indicates that you've reached the end of that branch of the tree because we've hit two nulls. And I'm going to use this tree for visualization on the slides, mostly because I like the way this one looks, but I've confused students with this in the past, so I want to show that left and right don't either, the tree that I use, they're either both references to nodes or both null. That doesn't have to be the case. We could have the case where left is a reference to a node and right is a reference to null. Left is a reference to null and right is a reference to a node. Or left and right are both references to null, or left and right are both references to nodes. All four are applicable. They're very much valid. So don't get caught up in the trap in your code. Even with this warning, so many students make this mistake anyway, of checking just left or just right for null. So just like linked list, we're going to check for null all the time. Since we can have nulls, we want to say if it's null, don't go over there because there's no object on the heap to go over to. So if it's null, don't go over there. But don't get into the trap of saying if left equals null, then there's nothing left to do. Because that's not necessarily true, because right could be referring to a null, to a node. Likewise, don't check if right equals null, then stop everything, because left could be referring to a node. You do have to check both of them, because one or the other could be a reference to a node. So if you're checking if it's the end of that branch, you need to check is left equal to null, then is right equal to null, and if both of those are true, then you know you've hit the end of that branch. But I'm going to use this one just because it looks prettier on the slide. It's what we call a balanced tree, where it's nice and balanced, it's symmetrical, looks nice on a slide. So I'm going to stick with this one, just for the examples. And here's some code. So to build that tree that we saw on the previous slide, this is the code that would make that happen. So a binary tree node is going to take a type parameter, again, just like our linked list. So hopefully you're all up to speed on linked lists by now. Usually these are separated by 3 weeks, but of course now it's 3 lectures. But hopefully that's still enough time to have linked lists down very solid. We've already had the quiz on it. We've already had the expected deadline passed for that homework. So hopefully we're solid on linked list nodes, because I'm really going to depend on that understanding, or you have no chance of understanding binary tree nodes. You got some catch up to do. But binary tree nodes are going to take a type parameter just like linked lists. So we can have a binary tree node of any type that we want. We're going to have the value, which is a variable that stores a value of that type, or rather a reference to an object of that type. And then 2 binary tree nodes of that type, left and right, instead of just a linked list node of A. Actually, I think it was T. I think I used T for the binary to the linked list node, and just a reference to next. Now we're going to have 2 binary tree nodes, references to 2 binary tree nodes, which can be null, which are left and right. And then a constructor to set our 3 instance variables. Nothing new there, nothing magical there. Just the standard constructor that takes parameters and sets the values of those parameters equal to the instance variables that we created. And that's our whole binary tree node. And unlike linked list node, where we put a lot of we put some methods in here in the binary tree node, for our linked list node we put a lot of methods in here. For our binary tree node, this is it. This is the whole class. We're going to leave it at that. We're going to add some getters and setters for value left and right, but we're mostly going to leave it just like this. And then we're going to write our algorithms outside of the binary tree node class. So to use this binary tree node class, this is a main method inside the binary tree node class. I just have it separated on the slide. I don't know why I even do this. I should just show the main method inside there. So I am able to access these private variables directly because this is in the same class, despite how it looks on the slide. So I am allowed to do this. And what I'm going to do is build my binary tree manually. So with the linked list, we wrote an append method, and we kind of prepended manually. The very first time we saw a linked list, we prepended manually like this. And then when we got to stack, queue, and linked list of doubles, we started prepending with a method call. For our trees, we're always going to, I can't say always, but for a tree to start, we're going to build them manually by setting the instance variables directly, and eventually through setters. These could be setter method calls, just the same. And when we get to binary search trees, we will actually write an insert method to follow the binary search tree thing. But that's, I would say next lecture, but that's in like an hour. We're going to see that. So we're going to build it manually. So what I'm going to do is create a new binary tree node where the value is 5 and left and right are both null. So I'm going to say this is just a single node with the value 5 and references to null and null. And that's going to be the root of my tree. And that's actually going to stay the root of my tree, where we replace this variable when we created the linked list. We're doing things a little bit different with our binary tree, where we're going to say root dot left. We're going to take that variable left that currently stores null, and we're going to replace that null with a new value, which is a new binary tree node. So we're calling the constructor again, creating a new node with the value 2, null, and null, and replacing left with that value. So effectively this null that we had right here is going to be replaced with this new binary tree node. So it actually refers to an object instead of just null. Same thing with the right. We're going to replace the right variable, effectively this null that went into the right. Why do I do this out of order? The right variable, and then replace that right, which does store null right here, with a new binary tree node with the value 8, null, and null. And then I'm going to do root.left.left. So root.left, so whatever node I replaced the left with, and then dot left, replace that null with this value, with this node, and then same left.right, right.left, right.right, and keep replacing those variables, replacing those nulls with new nodes. And this will create the exact same binary tree that we saw on the previous slide. I'm creating the root with the value 5, null, and null. And then I'm saying, hey, left, instead of referring to null, you're going to refer to a node with the value 2, null, and null. Right, you're going to refer to a node with 8, null, and null. And then left dot left equals a node with -3. Root dot left dot right equals a new node with 4, null, and null. Root dot right dot left equals this node with 7, null, and null. Root dot right equals this node with 14, null, and null. So we built this tree on this slide using this code to add those nodes one at a time into the tree. And that's really the crux of it. That's most of it. It's taking your understanding of linked lists and expanding it to now we have 2 references instead of 1. So depending on your understanding of linked lists, this can be very easy to make this leap or very difficult if you're still a little fuzzy on linked lists. So I'll wait here for a minute or so because that's kind of a lot to throw at you right away, and that's really the crux of it. That's binary tree nodes. The rest of this whole lecture is explaining the implications about it and algorithms to work with this. So I want to make sure we're comfortable with what a binary tree and a binary tree node, or what those things actually are, before we just plow through the rest of the lecture. So if there are any questions, let me know. Or if you have questions about linked lists, if there is something that's still fuzzy about linked lists, I would happily answer those questions as well. I don't know how long I can stand just sitting here silently staring at my computer, but I'll wait at least for the delay, the lag, which is about 22 seconds, I think, right now. Okay, I can't stand that much longer. If there are questions, I'll take them as they come in. All right, so tree traversals. How do we do anything with these trees is our big question. We have the tree structure, fine, but like our linked list methods won't work. Our linked list methods said if next is null or if this node is null, depending on how we have our method set up and our recursion set up. We said if it's null, makes sense to me. Nice, thanks, Mousebell. Then we've reached the end of the list, and if we haven't seen the end of the list, then make the recursive call. And that was it. That was our linked list methodology. If null, we're done. If not null, recursive call. But that's not going to work with trees because, well, we could say if both nodes are null, both left and right are null, we've reached the end, but then we have multiple paths that we have to traverse through the tree. And more specifically, let's answer the simple question. Nice. Thanks, Unknown Mischief. Thanks for letting me know, because I never know like if everybody's confused or not, or if everybody's completely lost, or if everyone's completely bored. I can never tell if it's either of those two things, because in both cases, whether it's online or in person, nobody says anything. It's only when we're in between those extremes that anybody will say anything. So thanks for letting me know. So let's try to do the simple thing of just visiting every node. What I want to do is just print the value from every node to the screen. That's all I want to do. Just something so we can know that we can traverse the tree. And of course, we're going to call them traversals. So how can we just visit every single node in a tree and make sure that we didn't miss any and make sure that we didn't visit any of them twice? How are we going to do that? It's the same thing. The first thing we did with the linked list, we just wanted to print every value. We did toString, and we just printed every value to the screen. Let's do the same thing and see how we're going to do that. And it's actually not that difficult, code-wise. The concept, we'll go through visualizations and stuff. But code-wise, instead of making a recursive call on just the next node, we're going to make 2 recursive calls to make a recursive call on both the child nodes. So we got 2 references to 2 nodes. Why not just make 2 recursive calls? QED, problem solved. And we're going to see 3 different approaches for this, either a pre-order traversal, in-order traversal, and post-order traversal. So let's talk about what those 3 are. And let's see them in code. So we're going to do this effectively like a toString. We're going to create the string, concatenate all the values together, and then return that string, which I kind of wish I should have updated these slides. When we get to the memory diagram, I'm just going to print to the screen instead of doing a toString method. But because it's just a little less moving parts to keep track of. But we're effectively going to do toString here. So we're creating our output string. We're going to make the recursive call, this in-order traversal, make the recursive call on the left node. Then visit the node that we're looking at, that we're currently visiting, visit its value, so convert its value to a string, and then make the recursive call to the right child node. So this is what we're going to call an in-order traversal. We're visiting all the node values, and we're going to do this, in order. We'll see what that means by the end of this lecture, but in order. And the big question here is, when do we make the recursive calls and when do we visit the node? So an in-order traversal, we're going to make a recursive call, which is going to visit the left child. And really, it's going to visit the entire left subtree. So if node.left was the root of a tree, visit that entire tree. And then we're going to visit the value at this node, and then we're going to visit the entire right subtree through a recursive call. So we're going to make a recursive call on the left child, visit this node, recursive call on the right child. And spoilers, the other 2 traversals, we're just going to move this call either before the 2 recursive calls or after the 2 recursive calls for the pre-order and post-order respectively. So what we're doing is building our string, initializing our string, concatenating all of the values from the left subtree to it, concatenating this node's value as a string to it, and then concatenating everything from the right subtree to that string, and then returning that string. And we're making the recursive calls using a reference to the node, to the left node or the right node. And apparently I lied. This is still in the binary tree node class because I am accessing left and right directly. I thought we put that in a different class for our traversals, but I guess not. So I misremembered. Sorry about that. But these recursive calls are on the node's left child and right child directly, which can be null. So node.left might be null. Node.right might be null. And you might be tempted to say if node.left equals null, don't make a recursive call, which is perfectly fine. That's fine to do. The way I chose to do it here is making the recursive call on something that could be null. So I have to be aware in my method that node can be null. So if I have node which is not null, but node.left is null, when I make this recursive call of the method, node is going to be null if node.left is null in the previous stack frame. So I can get a parameter equal to null in this method, so I have to have my null check. Did I get a node that's equal to null? If it's not null, I want to do my thing. But if node is null, I'm going to hit the else and just return nothing. And that's my base case of my recursion. Recursion always, always, always has to reach a base case or else it's going infinite. Just like writing a while loop has to reach a point where the condition is false or else it's going infinite. Or if you have a return statement somewhere in there, I guess you can get around that one. But you have to get a base case eventually with recursion. And that's when you make a call where node is null. And then we're just going to return empty string. There's nothing there. It's an empty tree. Null is basically an empty tree, just like null was an empty linked list. So we're going to return nothing. And we make our call. We're going to print out the traversal, and it should return the entire tree as a string, and then we can print it to the screen. Should be space separated values. Pre-order traversal, pretty much the same exact thing. We treat these as three separate traversals, but they're all the same concept. Pre-order traversal, I mean, minor differences, and they're depending on what you want to do, you might use a different traversal. We're going to see in order being pretty useful. We won't really see examples of pre-order and post-order. There are use cases that come up. We just won't see them in 116. So with a pre-order traversal, we're going to visit this node's value and then make our two recursive calls. Post-order, we're going to make our two recursive calls and then visit the node, the value at this node. So the difference between our three traversals is when we're visiting the node, either before the two recursive calls, in the middle of the two recursive calls, or after the two recursive calls. Other than that, they're doing the same thing. They're just visiting nodes in a different order. All three of these will guarantee that we're visiting every single node exactly once. Through the magic of recursion. So for now, we're going to go through a memory diagram and see how these work in action. But for now, just believe me, trust me, I guess, that these will visit every single node in the tree exactly once, and they will do them in specific orders that are going to be relevant depending on which one of the three we use, with like, what is this, 7, 5, 6, 7, 8, 9 lines of code, and a few of it's just a little bit of overhead. Creating this empty string we wouldn't have to do. Really 3 lines of true action, and then a little bit of overhead. Not much code to get these traversals working, but this little bit of code does a lot of work for us by traversing these trees. And that's the power of recursion. So this is the point where if you're not using recursion, if you're not embracing recursion, because I know a lot of you like to get through the linked list node, the linked list homework task 3 without using recursion, even though I say get your practice with recursion now because you're going to need recursion for trees. This is it. This is where you're going to, need is a strong word, but this is where you're going to want recursion. So hopefully those of you who did actually practice recursion on your task 3, you'll be doing pretty good here. If you didn't get any practice with recursion, if the first recursive method you write is in task 5 when you're traversing a tree, it's going to be tougher for you. But my challenge to you, if you're just a complete naysayer on recursion, if you're like, I ain't learning recursion, no way, no how, fine, do it. Write one of these 3 methods without recursion. It will take you more than 7, 8 lines. I guarantee you that. It's going to definitely be more than 3 lines of pure action, because you could write this in, well, you need the conditional too. If this were strictly printing to the screen, which it's actually going to be in the memory diagram. I got too many slides before that. In the memory diagram, it's going to be if node not equals null, print to the screen, recursive call, end of method. Closing brace, end of method. It'll be 5 total lines. It's going to take you more than 5 lines, I guarantee it, to write these without recursion. But if you're just like, nope, I'm never learning recursion ever, I can do everything with a loop, do it. Write one of these with a loop. Do it. I used to say nobody's ever taken me up on this challenge, but I have finally gotten 3 students actually now have taken me up on this and showed me some really neat code that does handle it. So if you are looking for a challenge, if you're like, you know what, I'm cool with recursion, but I do want a challenge because challenges are fun, go for it. I've seen some really unique, really fun solutions about this. If you are going for the challenge, I'll give you a few hints on how to get started. Is the reason why recursion makes this a lot easier is because the stack and the stack frames are keeping track of a lot of information for you. Namely, they're keeping track of how many times, not necessarily how many times, but whenever you visit a node, where are we with that node? So for like an in-order traversal, each time this stack frame gets control, it's either the first time it's been called, it needs to check for null and then make the left recursive call, or it gets back to this node after the left recursive call and it needs to visit its value and make the right recursive call, or it's coming back from the right recursive call and it's done with everything and needs to return. And we're using the stack, the program stack, to keep track of all that. So if you're taking on the challenge, you'll want to create some sort of stack that's going to remember the order in which you should be visiting the nodes, because your program stack isn't going to be doing it for you like it does with recursion. And you want to be able to somehow track, okay, this node's at the top of the stack. Is this the first time I'm visiting it? Is it the second time I'm visiting it after the left recursive call? Or is it the third time I'm visiting it after the right recursive call? So you have to keep track of all that. You have a lot of bookkeeping to do to keep track of all of your information about how much you've processed each node. So it's quite a bit of work to write these, which are the simplest tree algorithms that you'll write. Pretty difficult to write these without recursion. Definitely possible. You can do it. Anything's possible. But the recursion does a lot of the heavy lifting for you. So why not take advantage of the recursion? So let's take a look at our 3 traversals on our tree. And I'm going to draw the tree a bit different visually, just to clean it up a bit. Just have the value of the node, and if it's a reference to null, I'm either going to put these boxes, or eventually I'm going to not draw these boxes at all, but these boxes are representing null. And if there is a node that it refers to with left, there will be a line just pointing to the node. So just a little bit different representation. With an in-order traversal, we're going to call this on the root, in-order traversal on the root. So the root is this node here. It's not null, so we're going to go to the left, make a left recursive call. We're going to visit this node. It's not null, so it's going to make a left recursive call. We're going to go to this node. We have 3 frames on the stack at that point, all of them at this first recursive call. This one's going to make its recursive call on null. We're going to get this is false, so we're going to return. Get back to this node. This node was waiting for this recursive call, so it goes on to the next line, concatenates its value to the string, which will make its value the very first one that ends up in that string. And then go to the right, which is null, that returns. We go back to 2. Visit that node because it was waiting for its left recursive call. So visit 2. Then make its right recursive call. Recursive call, visit 4. Recursive call, return. Return. We're done with 2. It got its right recursive call. Return back to the root. Print the root, or concatenate it to the string in this case. And then the root is going to make its right recursive call and do the same thing over on this tree. So -3, 2, 4, 5 is the order in which we visited the first 4 nodes. Then on the subtree, we're going to recursive call, visit, recursive call, visit, recursive call, visit, recursive call, and then returns all the way back up. So we're going to visit them in order, which means everything on the left, 2, -3, 4, then the node, 5, and then everything on the right. So it's 8, 7, and 14. So the node is visited right in the middle of its left subtree and its right subtree. And that's true for every node because we're making the recursive calls to make that the order in which they'll be visited. Pre-order, visit the node, and then make your recursive call, visit the node, then make the recursive call, visit the node, recursive call, return, visit the node, and so on. So we're visiting the node before the recursive calls. We get a very different order that we're visiting the nodes in. In post order, again, a very different order that we're visiting the nodes in. Make a recursive call, recursive call, recursive call, recursive call, and then visit our first node, -3. Recursive call, visit 4 is the next node. Then get back to 2. So we're visiting everything in the left subtree. Then we're going to visit everything in the right subtree. And then with a post-order traversal, the root is always going to be the last thing that's processed after all the other recursive calls are done. All right. So that's kind of my hand wavy-ish, I guess, kind of talk through these. So now let's really hammer this down with a memory diagram. So we're going to see a traversal, another traversal, but I'll let you stare at this code for a sec. We're going to see another traversal. We're going to clean up the code a little bit and just print to the screen. Like I said before, we're not going to return a string and then just because it's a lot of extra stuff on the stack. It's a lot more clutter on the slide. We're going to change up the tree. I got to move my face. We're going to change up the tree. We're going to have a binary tree of strings and BT node instead of binary tree node. Again, just saving room on the slide. Binary tree node, the class is exactly the way it was. I'm going to remove all of the code here again for space on the slide, but it has value left and right as instance variables, and the code is going to be in the binary tree node class, so I'm able to access the instance variables directly. Why would you use pre and post order traversals? I'm always ready, well, not as ready as I want to be, but I always know this question's coming. I should just add some slides and show an example. So one thing that I used to show slides and I cut them for time constraints. One case I used to show in class is you can create trees. Actually, I'll leave that slide up. You can create trees to represent different types of data. Here we're just creating a binary tree of strings. We created a binary tree of integers in our previous example. But you can create something called an expression tree where each node is either an operator, like plus, minus, divide, equal, divide, multiplication, exponentiation, any binary operator that takes two operands. And then the child nodes of that operator are going to be its operands, which can themselves be other operators. So in this way you can, and then the leaf nodes, if it's child nodes are null and null, then that better be a literal, a numeric literal, so we can start the process. So all your leaf nodes will be literal numeric values, and then all of your internal nodes are going to be operators. And you can represent any expression this way. And then if you do an in-order traversal, you're going to build and say you're just printing to the screen, and you'd have to add in parentheses at each recursive call. So unlike just printing to the screen, we would print open parenthesis and close parenthesis. But if you do that, if you traverse the tree in that way, you'll get exactly your what we call infix expression, which is how we're used to seeing math. If the equation is 2 plus 3, it'll say 2 plus 3. But there's actually other ways to represent equations. There's prefix and postfix, which happen to absolutely mirror the traversals that we have. So if we do a pre-order traversal on an expression tree, we're going to get exactly a prefix expression, which is you have an operator and then the two operands, which themselves can be other operators. So in the 2 plus 3 example, it would be plus 2, 3, which says execute an addition operation, and then the next two values. Actually, I misspoke there again. It can't be other operators. If you have an expression plus, the next two values will be operands, which will be numeric literals, and then that will evaluate, and then you'll have your next operator and just keep evaluating through the expression like that. The reason you might want to use prefix expressions is usually not for human consumption. They're really difficult to read unless you have a lot of practice with them. But they're for computer consumption. If you have a prefix expression, it's very easy for a computer to evaluate that. So you might want to represent your expression in an expression tree, compute the pre-order traversal to get the prefix expression and feed that to a computer, and then I feel like I'm missing some details here. I might have got something wrong and all that. And then do the in-order traversal to send the equation to a human for human consumption. So you can represent the single equation in multiple ways using using an expression tree. So that's one thing. And there's postfix notation. I feel like it might have been postfix that we used. Postfix notation instead of prefix. I think that's where I messed up. So you have operand, operand, and then operator, which evaluates on the two previous values, which are the two operands. But anyway, that's one way you would use them. And there are other things, I don't know off the top of my head, but there are other cases where it crops up, where you'd want to use a pre and post order. That's something I'm told anyway, I don't know firsthand, I should look into it someday, that people who write compilers and interpreters, that they use, that they evaluate expressions in strange ways like that, and it's helpful. All right. So let's go through this memory diagram. Let's get this one started. So it starts off just like any other memory diagram ever since the class's lecture. We're going to call a constructor, get an object on the heap. We're going to write the type, make up a number for its reference. This is in the constructor stack frame is going to be a reference to the object being created. We have our we have our parameters in the stack frame, and in this case, those parameters all become instance variables in the code that's removed. But we've gone through this enough. Hopefully, you don't need to see that code again. We got the instance variables which are being created and getting assigned the values of the parameters. So we created this new node. This we've all seen, then returned it to root. We've seen that it's object creation. I don't have much to say about it, but we created a node with the value day, and I'm going to visualize our tree over here, what it looks like in a visual format. You don't have to draw the tree in your memory diagrams. If you find it helpful, by all means, go for it. But we won't grade any visualization of your tree. We're going to grade your memory diagram. All right, and then so things get a little bit different here. So this one, I have a little bit to explain. The constructor call is all the same. We're going to create a new node, stack frame, object on the heap. But we're doing root.left, so just in case, because this can be confusing, so let's explain it now that we have the visuals of the memory diagram. We're going to say root, which is this variable that's storing a reference to this node. We're going to say root dot always means follow the reference, which is why those of you on test 3 getting null pointer exceptions, if you have null, like root.right is null, if I am at this value of null and I say dot always means follow the reference. If the value is null, that's not a reference, and you're going to get a null pointer exception every single time. So we're careful not to do that. We check for null. If it's null, we're not going to use the dot operator. We always want to check for null. If we have something that could be null, check if it's null first. If it's not null, then we can safely use the dot operator. But if it's null, in this case, we're just going to do nothing. So root.left, root dot, follow the reference, left equals, so we're at this variable right here, and we're using the assignment operator, and reassigning its value, so we're going to replace that null with the new node that was returned. And I'm drawing my return arrow to the variable that it's returning to, and that variable happens to be on the heap, so I'm going to draw that arrow to the heap. So I'm replacing whatever this returns is going to replace the value stored in this variable, and it replaces that null with the reference to the node that was just created. And this is the way we create our tree in memory, to be able to have our nodes refer to other nodes and build the whole structure. And visually, this node, its left, is a reference to this node with the value have. So we have this as our tree where day is the root, because that's what's stored in our variable, which I happen to call root, but this variable, of course, can be whatever you want to call it. My binary tree will be fine. Creating another node. So root.right, root.right. So this is where our value is going to go. And then do our regular constructor stuff. I chose 480 for this node. And then replace that null in right with 480. So now we have this node root as a node with the value day, root as the node with the value day. Its left is a reference to a node with the value have. Its left is a reference to a node with the value have. And its right is a reference to a node with the value great. right is a node. Its right is a reference to a node with the value great, and then both of those child nodes have left and right of null. So have and great, these nodes don't have any child nodes. Here I'm not writing anything for the nulls, where I had empty boxes before, or I had explicit the word null. Here we're just not going to write anything. If I don't show anything, that means its left and right child are null. And then root.right.left. The very first time, this might be a little confusing, so let's walk through it briefly. I don't think it's too confusing at this point. We've seen references for quite a while now. But it could be a little... Ooh, I do have a node that's... Where does my face hang out for this example? Maybe I'll just go smaller. That'll be fine right there. So root.right.left. Root dot right dot left. We're at this variable right here. That just means follow the reference. Again, I like to just turn my brain off a little bit when I'm doing these memory diagrams. I'm at root. I'm at its value. So its value evaluates to OX350. Dot. Follow the reference. Right. And I'm at this object at this point. So I'm looking for a variable named right. Then dot means follow the reference. I'm at the variable right, so that variable evaluates to OX480. The dot takes me to the object OX480. So I'm at this node. And then left. Left, I'm at this object right now. I'm looking for a variable named left. I find it right here. So that's the variable that's on the left-hand side of the assignment operator. So this is the variable that's going to get a new value. And then on the right-hand side, we have a constructor. We do all our constructor stuff. And whatever reference we return from the constructor goes into that left right here and replaces that null with a value. So effectively, the roots right dot left got assigned a value of this node with the value A. So hopefully, if there was any confusion on how we're creating these trees, I hope that all this clears it up. I think it does. It ends up being a lot, looking at it, it does look like a lot, but a lot of it's very repetitive. The three arrows, figuring out where the three arrows go is really the only new stuff. The other is doing calling a constructor 4 times. So hopefully not too confusing. And the rest of the action, all the good stuff that we want to talk about, is going to go right here. So let's do that. Traversal of root. And this will be a post-order traversal. I just called it traversal again, space on the slide. I don't want to clutter things up, especially because I got to fit post-order traversal right here, and it would have made me make this box smaller. Just doing that for the slide, but I'm going to call it traversal. But since we're making the 2 recursive calls and then visiting the node, this is going to be a post-order traversal. So we're going to visit each node after both recursive calls. And who's ready for that? This, in a spring or fall semester, this lecture has too much stuff in it. I got to rearrange this week. And in the summer, it's going to work great, actually, because I can just take away from Friday's lecture, which is a little light during the semesters. But right here, I'd be ready to show a lecture question, and it's just not enough time. All right, so let's start. We're just getting into the action here. So let's call traversal. We're going to get a frame on the stack. Traversal takes a reference to a binary tree node. And since this is a static method, we are going to bring back static here. Since this is a static method, I'm not going to put anything in the stack frame for this. We're not going to have a reference to this because there is no calling object. We're calling this through a class. So I'm not going to have a reference to a calling object because there is no calling object. I'm calling it through the BT node class. So we're going to call the method. Just like before we knew what non-static methods and classes and objects were, we didn't put this in any stack frames. That's why this isn't going in this stack frame, because we are going back and revisiting static methods for this example. So traversal is called with node equal to root, where root is OX350. So node is OX350. If node not equal null, node does not equal null, it is actually a reference to an object, then we're going to execute the code inside this block, this conditional block. The very first thing this code does is makes a recursive call on node.left. Node.left is OX200. So we're going to get a recursive call of traversal where node is OX200. This call of traversal is going to check is node not null. I should have just wrote if node equal null. Well, I guess that would have been more code. So the node is not null, so we're going to execute the code in the conditional, which is going to make a recursive call of traversal on node.left. So node.left is null. We're going to make a recursive call where node is null, which we're going to hit our base case and it's going to do nothing. But I want to talk about what's going on right now briefly, because here we're really going to see the stack in action. Right now we have 4 frames on the stack. We have the main stack frame, which we're mostly going to ignore throughout the rest of the example, but 3 stack frames of traversal, all sitting here waiting for control of the stack. Well, one of them has control of the stack. A stack, only the top element can be accessed or removed, and we can only add to the top of the stack. So we have these 2 nodes sitting here waiting. Well, this this stack frame is the top of the stack. So this is the active stack frame. And these 2 stack frames are just hanging out, waiting for their turn to be on the top of the stack again. Once they're at the top of the stack, their job is to remember where they were and pick up right where they left off. So this node is sitting right here, waiting for this call to resolve so it can move on to its next recursive call. This stack frame is sitting in the same spot. This stack frame is the active stack frame, which will always be the green arrow in my memory diagrams. And it's about to end. It's about to return and be removed or popped off of the stack and give control back to this stack frame. And then we have our main stack frame, which doesn't get its own box. We have our main stack frame sitting right here on the initial call that triggered all of the recursion. So this stack frame, it's null. There's nothing to do. No code executes after the conditional. And it's removed from the stack. Remember, when we cross out a stack frame, it is actually being removed from memory. It's being popped off of the stack. It doesn't exist anymore. This variable doesn't exist anymore. This frame now is the top of the stack again. So it regains control over the program. This is the stack frame that's controlling our program right now. And it's saying, okay, all right, I got that returned. That I created a stack frame called the method traversal of node.left and gave it control of the program. I pushed it on the stack. I gave it control. It returned, and now I'm on the top of the stack again. Let me pick up where I left off and make the recursive call on my right child. So node.right, we're going to make a recursive call on null and put another frame on the stack. It's going to put another frame with null on the stack. That frame also does nothing and says, here, you can have control right back. I'm going to pop myself off the stack because I'm done. And now this node gets control for the 3rd time. Each node's going to get control 3 times, well, except the null calls, because they just don't do anything. They only get control once. But this node's getting control for the 3rd time, and it remembers where it was. And that's going to be the key thing as we go through this memory diagram. Each stack frame remembers where it was. So it remembers that it was on this line, waiting for this method call to return. Now that it did, and it has control, it's the top of the stack again. That means this method call returned. Now it's ready to move on with its code, and it's going to print out its value and then a space to the screen. So each node remembers where it was, where it left off. And when you get into 220, you'll get into more of the nitty gritty details of how stack frames, all the information that's in a stack frame, what it remembers. But one of the things it remembers is called a program pointer, which remembers exactly where it is in the execution of its code. So it knows when it gets onto the top of the stack again, where to resume. If you're taking on the challenge and writing this without any traversal, without recursion, that's something that you'll have to keep track of. You'll have to do the job that the stack is doing for us here, because the stack only does that for us with recursion because we have the stack frames and the program pointer. We're leveraging all of that information. Whereas if you don't use recursion, you have to keep track of all that bookkeeping, remembering where the node is in its execution, what code to check next once it's on the top of your stack. Again, is it the first, second, or third time? First is pretty easy to check. Okay, well, I'm adding it to the stack, so it's the first time. But whether it's the second or third is a little trickier. Not too tricky, but like it could be a programming task to do that. Maybe borderline. I don't know. But definitely a lot more work than the recursive solution. So it's going to print have to the screen and then return. And now this stack frame says, whoa, I got control again. Finally, it's been so long. This stack frame saw 3 other stack frames get created and destroyed. It's finally the top of the stack again. Remember, these crossed out stack frames do not exist anymore. We cross them out in our memory diagram so we can maintain the history of the program, but they actually don't exist anymore. They're erased from memory. The computer erased them from memory. They don't exist anymore. So really, it's root with OX350. All these constructor stack frames are gone. The very next memory address is going to be the stack frame for this traversal call. That's what's actually happening in memory. But our memory diagrams, we want to remember all the history. We want to remember those fallen stack frames that sacrifice so much for us. So here, this stack frame gets control again. And it says, okay, well, I just made this call, so the next thing I'm going to do is make my next recursive call. I'm going to go to node.write, that's OX480, put a recursive call on the stack with 480 as its parameter. And then that stack frame starts at the top again. The node is not null. It's 480. It's definitely not null. So we're going to run some code. We're going to make the recursive call on the left. So node.left is this 936. 936 goes on the stack. It's going to make a recursive call on its left, 936.left, because the node is not null. And then that node is null, so it's going to skip everything, not do anything, and return. We get control back to this stack frame. This is the top of the stack again. And it just made this left recursive call, so it's going to move on to its right recursive call. It's going to put another recursive call with null on the stack. And right here, I want to chill out for a bit and stare at this. So right at this moment, this snapshot of the execution of this program, this is as complex as this program gets. So I just want to take a breather and recap what the hell is even going on in memory at this point in time, at this snapshot. Because if you understand everything that's going on right here, then you got this. You're ready for the quiz on binary trees, which is Friday. Oh, or Thursday. Oh, that is true. You only really get two days to study this. Did I realize that? I must have. It's just there's not much time in the semester to do this. Yeah, that is the way it works. But then for graphs, you do get the Thursday to Tuesday to study. Yeah, this one I just couldn't do it any other way, could I? So at this snapshot, if you understand all this, you're ready for that quiz on Thursday. By the way, the trees quiz will look very similar to this. I'm not going to pull any punches. I'm not going to throw anything too weird at you. It's going to be manually creating a binary tree like this, and then doing something at least similar that shows the concept of a traversal. It won't be a post-order traversal because that's the one I'm using in lecture, but it'll be something very flavorful to one of the other two traversals. So nothing, no big surprises with that. We are, after we finish this memory diagram in this lecture, we are going to go on to binary search trees. I'm not going to put that on the quiz. The quiz is going to look like this memory diagram. So just know that for studying. If you ask me what to study, I know you didn't watch this part of the lecture. So let's analyze this memory diagram and take a look at what's happening right at this point of execution. We got arrows all over the place. We got different shades of gray. What the hell is going on here? So we have the original call we called traversal of root. That stack frame is still on the stack. That's been here the whole time. Ever since the main method created this stack frame, it's been sitting there with the reference stored in the variable root. It's been sitting there. It made a recursive call to its left that returned. Now it made its recursive call to its right. That recursive call is right here. And when this node gets to the top of the stack again, when it gets control again, it's going to know that this recursive call ended and that it's ready to print its value to the screen and then return. So it's almost done. It's like, I just got one more thing to do, but I need control again. But it's not going to get control until this recursive call finishes all of its work. So this recursive call made its recursive call to the left, and it's sitting right here waiting for this left recursive call to end. Its left recursive call is this stack frame right here. This stack frame got control, made its left recursive call, which returned, and now it made its right recursive call. So it's ready. It's just like the first recursive call. It's sitting there saying, I only got one more thing to do. Come on, right recursive call. Can you just finish up your stuff so I can do my thing? The right recursive call is about to finish. It's about to fulfill that. It's just a call to null. It's the base case. It's doing nothing. It's going to return control back to this stack frame so it can finish up. Then this stack frame can make its right recursive call and finish up. So this stack frame can finish up after its two recursive calls and its execution. So each stack frame is remembering where it is in this code, waiting for this recursive call to return or waiting for this recursive call to return. Yeah, all the quizzes are going to look the same. It'll be two memory diagrams, the one I just explained, and then that'll be your data structures 2 or DS2. And then your classes 2 is going to be inheritance. With inheritance, the big things I'm looking for are the super constructor call. Hopefully I said that enough times in the previous lecture that everybody's going to get that one. And also what method is called when you have overrides and inheritance. Which method's going to be called, which is going to depend on the type of the object and whether it inherited a method definition from its superclass and whether or not it overrode that definition. So just making sure you know where to look, that progression of which method is being called, making sure you know where to look for those. Those are the two big things I'm looking for. Those are the two big things I'm going to put into the design of that quiz to make sure you understand those things. But two memory diagrams again. And they'll be about the same size as the last one, as the linked list in the classes one. There will be just the nature of inheritance. There will be more code just because I have to have at least 3 classes and a main method to test anything, to assess what I'm assessing. But the memory diagram won't be too much bigger. It won't be too much more complex. All right, so I assume everybody's good on this snapshot, because I don't see any questions about this, so I'm gonna wrap this one up. So this node, it's the base case. It does nothing and returns back to this stack frame, which was waiting for its right recursive call to end. That ends, so it gets to print to the screen. It's going to print its value, node.value, to the screen, and return control back to this stack frame, which was sitting here patiently waiting for its left recursive call to end. So it moves on to its right recursive call, which is just null. That, as we know, is just going to return. The condition is false. Skip all of the code and just end. Returns control back. It says, wow, that was quick. Thanks for the quick turnaround, right node. and then goes on to its value and prints its node.value to the screen, followed by space. It returns, and then the main, the very first stack frame, the original one with the reference to the root, finally gets control back. Says, man, that recursive call took a while, which made many other recursive calls. That recursive call made 4 other recursive calls, either directly or indirectly. Finally got control back. It knew that it was waiting for its right recursive call to finish, so it's going to print its value to the screen. It's going to return. That return takes us back to the main method, so the main stack frame is now the top of the stack again. It gets control again, and it says, cool, I'm done, and just ends the program. So that's binary trees and tree traversals. Everything you need to know ever. If anybody tells you anything else, they're... I don't know. I don't even know how to finish this sentence. I don't know where I'm going with that. Everything you need to know. Not really, though. There's tons of other stuff to know. This is all you need to know for 116, though, about traversals and binary trees. If there are questions, let me know. I'm not going to wait for the latency. But if there are questions, I'll be happy to go back to previous topics. So that's everything you need to know about binary trees and traversals, but not everything you need to know about binary search trees. All right, binary search trees. And I think I can make my face a little bigger. Binary search trees is the next cool new thing we are going to learn. And let's learn them. And by the way, if you're wondering, well, I already told you what's going to be on the quiz for the trees quiz. But if you're wondering for future reference and stuff, I don't even have a memory diagram in these slides. I don't have a memory diagram about binary search trees at all. So that's your clue that I'm not going to throw a quiz at you where I expect you to write a memory diagram about a topic. So if there's any topics where I just completely omit the memory diagram, it means I'm not throwing a memory diagram at you on that specific topic. Like when we get to, for example, when we get, that's too far ahead. But when we get to graphs, I'm going to show a memory diagram about graphs, but I'm not going to do a memory diagram for binary search, or breadth first search. So that's, you can use that kind of as a clue. I'll always give you a memory diagram that's going to be quite similar to what's going to be on the quiz. Obviously not identical, but similar. It will show off all the concepts. All right. Binary search tree. This is it. Binary search tree in one slide. For every single node in the tree, all the nodes in the left subtree come before that node's value. And all the nodes in the right subtree come after that node's value. So this is a binary search tree using the less than operator as a comparator, where all the nodes in the left subtree are less than, all the nodes in the right subtree are greater than each node's value. And this property has to hold for every node. So it holds for the root, all these values are less than 5, all these values are greater than 5, but it also holds for these two nodes as well. So 2, so everything to the left has to be less than 2, everything to the right is greater than 2, everything to the left here is less than 8, everything to the right is greater than 8. And we have one decision. It's not critical to the concept of binary search trees, but when you're implementing a binary search tree, there's always the consideration of how do we handle duplicate values. If I want to add another 5 to this tree, should it go to the left? Should it go to the right? Or should I just not allow it at all? Some implementations just say, no, you can't have duplicates. For example, if you're building a binary search tree that's going to be a map, a key value store, you just, where the values are the keys and the nodes also have values, which are the values. That kind of breaks down since we call these values and they'd be used as keys. But you would just strictly not allow it. You say, hey, I already got that in my tree. I'll replace the value for it, but I'm not going to add a new node because I already have a node with that key. So you might just not allow them at all. For what it's worth, we're going to break ties to the right. So if I added 5 to this again, it'll go to the right. For what it's worth, in your homework, we're not going to, I'm going to leave it explicitly undefined in the homework. And in the homework it says, just don't test on duplicate values. I'm not going to test on duplicate values. You don't test with duplicate values. Then we don't have to add a little bit extra complexity to the homework where I say ties have to be handled to the left or ties have to be handled to the right, because I would just have to make that decision and then force you all to follow whatever decision I make. And I don't know if there's much educational value in that, just blindly following whatever I say. There's a little bit, but the homework's getting hard enough. Like, I don't need to add extra stuff to it. We'll just both agree to not test it. So in the homework, we won't have to worry about duplicates. And then we're going to use our comparators. This is why we learned about comparators in inheritance during the inheritance lectures. It's so we can use our comparators for binary search trees. Otherwise, I would have pushed comparators off to the polymorphism week. But we want them for our binary search trees. And here's our binary search tree. Most of it. I shouldn't say most of it. It's a very small portion of it. I don't know. It's the start of it. Let's leave it at that. So binary search tree is it's a data structure. It's gonna take our usual things. It's gonna take a generic type, which I named A here. It's going to have the root of the tree. It's gonna have that as a variable, the root of the tree as a variable. And just like our linked list of doubles, which I'm surprised how many times I got questions and amazement about that, where in office hours I'm like, the linked list of doubles was made to mirror the homework, which I said in lecture. Just go watch lecture before you ask questions. But anyway, and I don't have to worry about anyone being offended by that because they're the ones not watching lecture. So I'm going to store a binary tree node as the root of the tree, which the reason I thought of that is mirroring your homework. You're going to write a playlist class, and that's going to have an instance variable which stores the values that you want, which can actually store a binary search tree as a variable. So I guess your homework takes it one level further this time, that your playlist should have an instance variable of type binary search tree, and then you can use the binary search tree that we're going over in today's lecture to eventually sort your playlist of songs using a comparator. So we're going to have the root of a binary tree and a comparator, which we get from the constructor. The root, we're initializing at null. Technically, this is an optional line. Since I didn't initialize this, it will get the value null. But I like to be explicit about my intentions and say, look, I know root's getting the value null. I'm going to be very explicit about it. So anyone reading this code knows that it is intentionally getting the default value of null. And then the comparator is getting whatever we get in the constructor. So in your playlist class, you want to take the binary search tree class from lecture. Any code that I show in lecture and any code in the examples repo is always fair game to just cut and paste into your project. So you can take this binary search tree code and use it in your playlist. That's the intended strategy for the homework, is to use a binary search tree. And then the bulk of the difficulty of the homework, we'll have time to go through it and I can explain the homework. But the bulk of the difficulty is going to be traversing your tree. So I expect you to do a traversal on a binary tree and convert a binary tree into a linked list. That's where the bulk of the difficulty, I say difficulty, but the bulk of the education is coming from, is going through that practice of traversing a binary search tree and converting it to a linked list. The rest of the stuff, don't overthink it too much. Just use the BST code that you're given. Yeah. And then we're going to add 2 methods. So the rest of the class is going to be an insert method and a find method. These are the 2 things we want to do with a BST. So we already know what a BST is. Everything to the left comes before, everything to the right goes after, and we're breaking ties arbitrarily. They're going to the right in our implementation, as we'll see when we get to the insert and find. Actually, just when we get to insert, it doesn't come up in find. But these are the two methods that we want to write. I want to insert some value, and I want to find, which is just going to return a Boolean this time instead of returning a reference to the node containing that value. We're just going to return a Boolean to say, is this value in the tree or not? And we're going to find that. We're going to see a new trick with comparators here, which I explained audibly. It's not on my slides in the inheritance lecture, but we're going to see it in action this time of how to use a comparator to check if two values are equal to each other. Because we can't use the dot equals method because in your... Did I even do that? I don't think I asked you to find a value in the homework. But if I did, if I said, does your playlist contain a song with this ID? Why isn't that on the homework? I should put that on there. I'm pretty sure it's not. Does this playlist contain a song with this ID? We're going to call find with that ID, but this is going to be a reference to a song object, and the equals method is going to compare two songs by reference, which is not what we want to do. So we would have to use our comparator. If our comparator is sorting by the song ID or the song title, as it were, that's the comparator that we have, then we need to use that comparator to find out if the value is equal to each other. So let's write these methods. So here's how we want to use our binary search tree. We're going to create our binary search tree, an object of type BST. It needs a reference to a comparator. So here I'm going to give it our int increasing comparator that we saw from the inheritance lectures, which is the, or no, we didn't see this one. We saw int decreasing, which was greater than. Here we're going to do int increasing to get the default order of our integers, which is the less than operator. So we're going to use less than to do just standard sorting, what you would expect for your integers. So we expect these to be sorted -3, 2, 4, 5, 7, 8, 14. So we're going to insert all these values to build our binary search tree. And we're going to call find. 7, we expect true. 8, we expect true. 3, we expect false. We got -3, but no +3 in here. So we expect this to print true, true, false. And then we're going to run an in-order traversal on our BST. Now, an in-order traversal makes the left recursive call, visits the node, and then makes the right recursive call. I'm doing my hand backwards. If you can, it's barely on camera anyway. But you're making the left recursive call, visiting the node, and then making the right recursive call. Now, a BST says everything to the left comes before this value's node, this node's value. So we're going to the left, visiting everything on the left, and then visiting that node. And then visiting everything on the right, everything that's greater than. So we're visiting everything that's less, that comes before that node. I'll say less than just because it's easier, since we're using increasing in this example. We'll visit everything that comes before that node, everything that's less than that node, then visit that node, and then visit everything that's greater than that node. If that's true throughout the entire tree, which it's true because that's the definition of a BST, and through recursion, that's the order that we're visiting in as we visit every single node, guess what we're getting with an in-order traversal on a BST? We're getting those values visited in sorted order. So in-order traversal on a binary search tree, combining these two definitions, is always going to visit the nodes in sorted order, which is a pretty handy property to have. So our in-order traversal out of the three ends up being the most useful one, at least in CSE116, if we're talking about sorted order and things like that. For other applications, like I said, the expression trees, you might want to use a different traversal. But for our purposes here, what we're seeing in-order traversal is going to be our go-to traversal when dealing with BSTs. Okay, here's insert. Here it all is. I don't know if I should stop doing that or not, but I do like doing this, is show you all the code all at once and then spend a lot of time explaining it all. So here's all the code all at once. For insert, and then we'll do the same thing for find. So insert into a binary search tree. The big thing is, because we could just insert wherever. We could just look for any null and then replace that with a node. But what we want to do here, what we need to be careful about, is that we maintain the property of the BST. BST is short for binary search tree. I don't think I said that explicitly. Hopefully you could see that, but just in case. So BST, we have to maintain that property. That property, everything to the left less, everything to the right greater. We have to maintain that property while we're inserting nodes. So we have to be very careful about where we insert a node. We can't just insert it anywhere we want. We have to be careful. So the very first thing is if the root is null. So it's initially null. We set something to null explicitly. You saw this in your task 3. You all should be familiar with this one. That we set something equal to null to represent an empty binary tree. So whenever we're working with this root variable, we have to be aware that it might be null. Since it might be null, we're going to have our null check here. We're going to say, look, if it's null, I got myself an empty tree. If I got myself an empty tree, I know where to put this value. It's just going to go, it's going to create the tree. It's going to be the tree. It's the only node. I can't mess this one up. I'm going to create a new node, and that node is the tree, and it's going to be the root of the tree. So I'm going to set the root equal to a new node with that value. And despite my warning during the linked list lecture, I still saw this a lot, so I'll repeat it here. Never create a node, at least in 116, maybe if you have some really strange application in the future outside of this class where this comes up. In 116, you're never creating a node where the value is null. That's not how we represent an empty binary tree node. If I see root equals binary tree node of null, 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 I'll know you didn't watch this part of the lecture. And how many times I still saw new linked list of null, null to represent an empty linked list. That's not how we represent an empty linked list. It's not how we represent an empty binary tree. An empty binary tree is the root, the tree itself. It's just null, equal null. And then when we have a value, then we're going to replace that null with a new node that has the value that we're inserting, and left and right are both null. Now, that's the easy case. If the tree's empty, there's nothing there, we're just going to create the new tree. The more tricky case is the recursive case. The recursive case. The tree's not null, so we know we actually have a tree. So we want to write another method here. The reason we want another method is we want to set up our recursion, and our recursion needs to know let me back up a bit. We want to navigate this tree and move from node to node to find where this new node should be inserted. So we're going to navigate the tree, and we need to keep track of where we are in that navigation. Where are we in the navigation? So we want a parameter. If we're going to leverage recursion, now you could try writing this with one with a loop. This one's actually not too hard to write with a loop. This one's a lot easier than the traversals. But if you want to use recursion, we're going to need that node as a parameter so we can keep track of which node we're currently visiting, specifically because this code is not in the binary tree node class, so we can't leverage this. This is going to be a reference to a BST because we're in the BST class. If we're in the binary tree node class, then this is a reference to a binary tree node, and we can manipulate this to be a reference to the node that we're visiting. We're outside that class, so this isn't going to help us. That's the binary search tree itself. So we're going to take the node that we're visiting as a parameter. But the insert method doesn't take a binary tree node as a parameter. So what we do is write a helper method. When you're writing recursion and you really want access to some information and you don't have access to it, you want it to be a parameter, write a helper method with whatever parameters you want, whatever ones you want to be able to keep track of through the recursion. And then in the original method, call that method, call your helper method, with the initial value. So I'm initially going to start at the root. So I'm going to call my helper with the root and the value that I want to insert. Now that starts off my recursion, and now insert helper can be the recursive method that calls itself. And we do this. I know I went over this before, but it's one of them concepts that's worth reinforcing. The reason we do this is because insert, if you want to insert something to my BST, you want to use my BST class, and you just want to insert something. You're going to be inserting songs. You're going to create an instance of my BST class, and then you're going to be inserting songs into it. You just want to say, insert this song. And that's it. That's all you want to say. But in my recursion, I want to say, insert this song, and here's the current node that we're visiting, which is the candidate node where we're going to insert this thing. But when you're inserting a node, you don't want to think about this. You don't want to care about this at all. You just want to call this. So I'm going to make this method public and say, call this method. And then I'm going to set up my recursion by calling my private method, my encapsulated method, which is the hidden details of how the insert method actually gets the job done. So this method just exists for ease of use for the end user. And then this method is getting the work done with the parameter list that I want. So if you and your end user disagree on what the parameter should be, just write two methods. Simple as that. And then call the method. That's going to kick off our recursion. So we're going to start at the root node. And for each node that we visit in insert helper, we're going to use our comparator to check where this value should go. So we're going to invoke our comparator. We're going to compare the value that we're inserting with this node's value. Remember, our comparator returns a Boolean. It's going to return true if the first parameter, or argument, I guess, on the calling side, if the first argument comes strictly before the second argument, and false otherwise. So if this returns true, that means the value that we're inserting comes strictly before this node's value, or with our less than comparator, then to insert is less than this node's value, which means we got to be thinking left. Based on the definition of a binary search tree, if this value is less than this node's value or comes before according to the comparator that we have, then this value needs to go to the left of this node. So we're going to look left. We're thinking left at this point. So we're thinking left, and if we're going to peek over to the left. We're at a node. We know we need to move left, and we're going to peek left. If the left node is null, and now we're not inside the binary tree node class anymore, we're in the BST class, so we have to use our getters and setters. I don't think I showed them on a slide yet, but you can imagine what those are. In the binary tree node, we have getters and setters for value, left, and right. So if left is null, that means I'm thinking left, I'm looking left, and there's nothing there. Well, if there's nothing to the left, guess what? I just found where I'm going to insert this node. So if left is null, I found a home for this new node, this value that we're inserting. I'm going to create a node for that value and set the left of this node that we're currently visiting, whatever node it may be, to that new node with the new value. Now, if I peek left and left is not null, that means left is a reference to a node. I'm going recursive. I'm going to recursively call insert helper with the left node because I'm thinking left, I'm moving left, I'm going left, and I'm going to go left through recursion. Make a recursive call with the left node forward to insert, so it's the same value. The value we're inserting isn't going to change, and then move over to the left with recursive. And then if the comparator returns false, this node either comes strictly after the node I'm inserting, either comes strictly after the node's value at this current node, or it's a tie. And this is where we're making that arbitrary decision where ties are broken to the right. So if I'm inserting a value that's identical to this node's value, we're heading over to the right anyway. So we're going to go to the right, and this is where we could add code to not allow duplicates at all. And likewise, this is the same thing as going left. If the right is null, we found a home for this value, and we're going to put it there. That's our base case. We're going to end the recursion. Otherwise, we're going to recursively call to the right. And for what it's worth, this is tail recursive, so this will work on, this won't overflow our stack. That's a side note. If you don't want to think about that, don't. But this is tail recursive for those of you who want to think about that. Because the recursive call is the last thing that happens. You won't do anything with the return value. In fact, it returns void, so nothing else to do. There could be a line of code after this that makes it not tail recursive even with a void return, but in this case, that's not the case. It is tail recursive. Okay, so that's our insert. Visually, looks like thus. We're going to insert 7. If we want to insert 7 into this tree, we're going to start at the root, and we're going to ask, does 7 come before 5? So our comparator is the less than operator. So we're going to say compare 7 and 5. Those are going to be the arguments for the less than operator. So is 7 less than 5? That's going to be false. So we're moving to the right. We're thinking right. We peek right. It's not null. So we move over there in a recursive call. Then we're going to check, is 7 less than 8? That's true. So we're going to move left. We don't, and we do find null this time. So since the left is null, we're going to insert right there. We're going to say your left was null. Now it's going to be this new node with 7 and child nodes of null and null down here. Could you explain why this always works? Why do we never need to insert to a non-leaf node? Wait, could you explain why this always works? Why do we never need to insert to a non-leaf node? And I assume we got kind of caught up in the delay in the stream. So the node doesn't have to be a leaf, but like in this example, we don't have a leaf node. We do have a node with a value to the right, but since we're only looking to the left, we don't actually care or know that there's a value to the right. So it's not a leaf node, but we're still able to insert because where we were looking, we were peeking left, and left was null, we inserted to the left. So it doesn't have to be a leaf node. But of course, if instead of 14 we had null here, it would still work just the same. We would insert 7 right there. Likewise, if we want to insert 9, we would do the same thing. We would say 9 greater than 5, 9 greater than 8, 9 less than 14, and we'd add 9 right here. So we could always add that. We can always add a new value. If we want to add 3, less than 5, greater than 2, less than 4, null, add it right here. And it's always going to maintain that property because we're exactly asking, hey 5, how do we maintain your property? If we're adding, let's go back to 7. If we're adding 7, how do we maintain your property? Well, 7's greater than 5, so due to the property BSTs, it's got to go to the right. Hey 8, how do we add this 7 and maintain the property? Well, 7's less than my value, so it's got to go to the left. And then we find null and add it right there. What if I wanted to add 6? So, and I'll assume your question means after we add 7. So 6, we're going to say 6 less than 5 is false. So because 6 greater than 5, we're going to go to the right. 6 is less than 8, so we're going to go to the left. 6 is less than 7, go to the left. Left is null, so we found a home for 6, and we'd add 6 right here. Yeah, because if you mean before 7's added, it's the same exact thing as adding 7. And for what it's worth, just for kicks, let's add 14, just because to show ties. I don't know why, but 14 greater than 5, go to the right. Greater than 8, go to the right. And I'm even saying it wrong. Let me say it the right way. 14 less than 5 is false. 14 less than 8 is false. False, we always go to the right. 14 less than 14 is false, so we go to the right again. And our code actually doesn't care that it's a tie. Just the way it's implemented, it's not really important or relevant to BST, the concept. It's specific to this implementation. But 14 less than 14 would return false. We would go to the right and add 14 right here if we had that duplicate. It gets a little weird with 5. 5 less than 5 is false. 5 less than 8 is true, 5 less than 7 is true. If we had our 6, 5 less than 6 is true, and 5 would go over here, which would still work with the in-order traversal. Right? Would it? Wait, no. Yeah. Oh, yeah, it would. I'm like, it has to. But my brain had a little hiccup there. Because you would visit everything to the left, then visit 5, and then you go to the right, but you keep making left recursive calls until you found that 5. That would be the first thing printed, and then you'd start doing the rest of the stuff. All right. That's insert. The recursive calls return. They're returning void, so they just straight up end, and all the recursive calls end. Okay. I think we're good on insert. I think I spent enough time on that slide for questions. We got some good ones. But if, likewise, just like always, if you have questions on insert, I'm not going to wait for the delay. But if you have questions as they come in, I'll be happy to go back and answer them. But I'm going to move on with find if there are no questions. I'm going to move on with find, and if there are questions, I'll go back, I should say, to word that properly. But let's do find. And find is going to be pretty similar to insert. We're going to have a similar setup, at least in the beginning, but we're going to do a little bit different inside our helper method. So find starts off just the same. If the root is null, we have an empty tree. I don't even care what we're trying to find. We're returning false. And there is, just to really hammer home this subtlety, the value of our node should never be null. We don't initialize this to new binary tree node of null, null, null. That would not be an empty tree. That would be a tree of size 1 where the one element has the value null. The one value is null. Then, if value is null, we would actually find it in that tree. We'd go to our find helper and find that value of null. Well, our comparator would break because our comparator is not checking for null. But is it the less than operator might check for null? I don't know. But no, I don't think it would. But anyway, if it's empty, if the root of the tree is null, that's an empty tree which can't store null. So even if value is null, it's not in an empty tree. We can't find null in an empty tree because it's empty. It has absolutely nothing. It cannot contain anything at all. So we're just going to return false. It doesn't have any values. It can't have any values. Not even the value null. So initializing the value, this to a node with the value null is very different than initializing it to null. Initializing to null is an empty tree. Initializing it to a null node with the value null is a tree of size 1 that has the value null in it as one of its values. Very, very different things. But on the surface, when you first see it, they look very similar. Very, very different in practice. All right, so if the tree is not empty, we're going to make our recursive call. We have a helper method, so we have a reference to the node that we're currently visiting. We're going to call our comparator, and we're going to look for where this value should be. So when we were inserting, we were very careful to maintain the property of a binary search tree, where everything that comes before is to the left, everything that comes after is to the right. Now, on the find method, we're on the other end of that, where we're going to take advantage of that property. So if we're looking for a value that comes before this node's value, and this is strictly before, remember our comparator returns true if the first value comes before the second value, strictly before the second value, false otherwise. So ties are going to be in the false case. So if this returns true, that means 100% we're looking left. To find comes before this node's value according to our comparator. Therefore, we have to look left because of the property of BSTs. We have to look left. There's no other place that, like, if this value is in the tree at all, it has to be to the left. So we're going to peek left. If left is null, then we know this value has to be to the left if it's in the tree. And if we peek left and there's nothing there, well, toFind's not in the tree. Sorry, return false. We looked everywhere where it could possibly be, and it's not there. Otherwise, make our recursive call to the left. So each time we call this comparator, if this comparator returns true right here, for whatever node we're currently visiting, we're eliminating the entire right subtree. It can't possibly be over there. If toFind comes before this node and everything to the right of this node comes after this node, or tied in our case, then toFind can't be to the right. So we don't even have to look over there at all. No matter how many nodes are over there, we don't have to look at any of them because it can't be over there, because this is a BST. Because our insert method guaranteed it would have the properties of BST. So if this returns false, we still have two conditions. Either toFind comes strictly after this node's value, or this node has the value toFind. The values are equivalent. So let's invoke our comparator again. We're going to use our comparator again, but we're going to do something slightly different here. We're going to reverse the order of the arguments. So instead of saying, does toFind come before this node's value, we're going to say, does this node's value come before toFind? Now, since these comparators have to return true if this value comes strictly before this value, the first one comes strictly before the second one, then this is going to give us more information. This isn't the same call as the first one. Even though it seems like it's giving us the same information, there's one really important thing that it's telling us. It's going to tell us if these values are equal. So if, first of all, if this returns true, then that means this node's value comes before toFind. That means we're thinking right. toFind comes strictly after this node's value. So we have to look right. If it's in the tree at all, it's to the right. If right's null, this value is just not in the tree. Otherwise, make our recursive call over to the right. But here's where the magic happens. If this comparison returned false, and this comparison returned false, that means these values are equal according to this comparator. Doesn't necessarily mean the values are strictly equal in value, but according to this comparator doesn't care about the relative difference in ordering between these two values, which is a mouthful. But if we're thinking of our less than operator, if toFind is not less than this node's value, so this returns false, toFind doesn't come before this node's value, and this node's value doesn't come before toFind, this one returns false. If these both return false, the comparator is saying, nah, toFind doesn't come before this node's value, nah, this node's value doesn't come before toFind. There's only one other option. They're the same. Return true. We found what we're looking for. This is our value. So what I mean, so with integers, it's more clear. If this is 5 and 5, 5 is not less than, and we're using less than, 5 is not less than 5, 5 is not less than 5, so we must have the same value. What I mean by they don't have to strictly be the same is you have a comparator, is that test 4? I guess a lot of you haven't gotten quite that far yet. But in test 4, you'll have a comparator that compares two strings while ignoring case. So we might have the same characters, but one's all lowercase and one's all uppercase. They're not equivalent. They're not the same value, but according to a comparator that's going to compare two strings alphabetically but ignoring case, those are going to be treated as the same string according to this comparator, and it'll still return true. So doesn't have to be strictly the same value, but according to a specific comparator, that comparator can say, I don't care about the difference between these two. If I have one word that's capitalized and the same exact word but not capitalized, that comparator that ignores case is going to say, I don't care about the order between these two. They're effectively the same according to that comparator. Okay, let's see this in action. We got our binary search tree here. We're going to find the value 4. And we're going to use our less than comparator. So is 4 less than 5? Does 4 come strictly before the value at this node? We get a true, so we're looking left. We're going to peek left. It's not null, so we're going to recursively call over to the left. We're going to ask, does the value I'm trying to find come before the node that I'm looking at? Is 4 less than 2? We get a false, so we're going to do our next check. We're going to reverse the order here and say, well, does the value at this node come strictly before the value I'm looking for? And then we're going to get a true, so we're going to move right. When we get to the right, we're going to say, hey, does the value I'm looking for come strictly before the value at this node? And we're going to get a false. Comparator's going to be like, nah, bro. And then we're going to reverse the order. We're going to say, well, does the value at this node come strictly before the value I'm looking for? Again, the comparator's like, nah, doesn't. So we're like, well, comparator, if the node I'm looking for doesn't come strictly before the value at this node, or the value I'm looking for doesn't come strictly before the value at this node, and the value at this node doesn't come strictly before the value I'm looking for, what's going on here? And eventually I'm going to go, oh yeah, they must be the same value. So I'm going to return true and say we found the value we're looking for. And notice in this first comparison, we did one comparison and eliminated all these. We never even have to look at these values. Because if we're trying to find 4 in this tree and the root's 5, if 4 is in this tree anywhere, it cannot be over here, or else we don't have ourselves a binary search tree. So we're leveraging the property of a binary search tree to get what we want. Oh, I only have one comparison in my slides. So let's do another one. Let's do 6. Let's try to find the value 6. So does the value I'm looking for come before this node? Is 6 less than 5? No. Is 5 less than 6? Yes. So we're thinking right. Is 6 less than 8? Yes. So we're going to think left. Is 6 less than 7? Yes. We get true, so we're going to look left. We're going to peek left. We're going to see null. So we're going to return false, return false, return false, return false. And we get false is the final answer. And just to circle back around to a point I said earlier in the lecture, because this will be important for your homework, is an in-order traversal on a BST is going to visit the nodes in sorted order. So if I call an in-order traversal on this BST, which happens to be in the when we first learned about binary trees in general without BSTs, I happen to use this example because it does happen to be a BST, just to foreshadow that. But this is a BST. We're going to call an in-order traversal. Start at the root. We're going to make a recursive call to visit everything that's less than this node. Then visit 5. So everything that's less than 5. Then 5. Then the right recursive call, everything that's greater than 5. It's going to visit in sorted order for every node. So when we make the left recursive call, we get to this node. We're going everything to the left. Then the node. Then everything to the right. Then go back to this node. So we're going to visit these nodes in sorted order because of the definition of a binary search tree. So we do get exactly our sorted order. We go left recursive call, left recursive call, left recursive call, -3, recursive call, 2, 4, 5, 7, 8, 14, and then all returns. Very handy property. So when you're converting your binary tree, your BST, into a linked list on the homework, think in order traversal. Hopefully that's a gimme of which one of the 3 traversals to use. Let's take a breather here, just in case there are questions. We'll shift gears a little bit here. We're going to talk about efficiency for a little bit. This is mostly foreshadowing 250. This is a little bit of advanced topic for 116, but it's something I like to talk about to address the question of why the hell would we even use a BST? Like, we have array lists. We can just sort an array list. Why would I bother? So I want to talk about some efficiency, just to talk about why we're even bothering showing you a new data structure. But let's make sure there are no questions or answer any questions that are about the strictly 116 concepts of what a BST even is. And what I mean by that is, like, quizzes. Well, you already know quizzes are all memory diagrams. Homeworks are all coding. Homeworks are all release. So I guess you already know this. But when I start talking about runtime analysis, there's just nothing in the assessment of this course where that would even fit. But usually we have interviews during the fall and spring semester. And I have to explicitly say runtime won't be on the interviews. I guess I don't even have to say that this semester. But I'm sitting here waiting for questions, so might as well say something. Okay. I'm too anxious to wait too long. If there are questions, let me know. I'll be happy to go back. All right. Efficiency. We got to talk about a little bit of vocab, a little bit of new concepts and definitions here. So we can talk about efficiency, and that's balance tree. I guess I already mentioned this a little bit, but let's give a little bit more formal definition on what a balanced tree is. And if it's what we call fully balanced, that means you have the same number of descendants in the left and right subtree. I briefly defined descendants earlier, but the left and right subtrees have the same size, is what a fully balanced tree is. And you usually don't have a completely balanced tree, but you'll have roughly balanced, roughly the same number of nodes. For example, if the number of nodes is not a power of 2 minus 1, you can't have a fully balanced tree. But if you're close enough, then it's considered to be balanced. If you have a BST that is balanced, then the number of nodes from the root to any null is O of log of n, and we call that the height of the tree. This is where it doesn't have to be perfectly balanced, but as long as it's balanced within some constants, the big O notation is going to eat everything else and say it's of the order log of n will be the height of a balanced binary search tree. Now, if the height of the tree is O of log of n, then insert and find are going to take O of log of n time. So it's log n time to insert or find in a binary search tree. Looking at think of these two methods, these two algorithms. Each time we do some constant amount of work, what we're doing is checking the value at a specific node and deciding where to make a recursive call, or we're just completely done. If we find the value we're looking for, we're just done. But we're making a recursive call. Worst case, we're going to go all the way to a null. In insert, we're always going to make it to a null. In find, the value's not in this tree, and we're going to make it to a null. So it's going to take log n recursive calls, because that's the height of the tree. So it's going to take O of log of n recursive calls to make it to that null to find that, hey, this value's not in the tree. And that's really efficient, as it turns out. And for what it's worth, we have a new sorting algorithm here. If we have a balanced binary search tree, and we insert n elements, insert takes log of n. We insert n elements, we just did n times log n work, and then we do our in-order traversal, which takes O of n time. We didn't talk about the runtime of traversals, but just visits every single node, O of n time. We have a new sorting algorithm that's n log n. So go us. We already had merge sort, but we have a new one, n log n. We can sort in n log n time. So big deal. We got another n log n sorting algorithm. What's the advantage of this? Well, it's that we can maintain a sorted order in log n time. So if we have a binary search tree, and it's all sorted, everything's nice, we inserted n elements, we sorted it all in n log n, and then we want to add another element. We can add that element, insert in log n time, and maintain that sorted order with a log n insert. If we wanted to do this with an array or an array list, it's going to take O of n time just to insert, Because worst case, what we're inserting is the minimal element. It's going to go in index 0, and we got to copy everything else down the array list. Or we have to resize the array list, which can take O of n time. We usually don't worry about that in asymptotics for reasons you'll talk about in 250. Talk about amortized runtime. But if you have to insert into index 0, it's O of n, not even O of n time, it's n time to move all those values down. So worst case is definitely n. Linked lists, we can insert very efficiently. We're just creating a new node and updating a few references. So that's fine. But it takes O of n time just to find where to insert. So if we want to insert and the value we're inserting happens to be the last element of the linked list, we have to navigate the entire linked list going get next, get next, get next, get next n times to find the end of the linked list until next is null, and then we can insert there in constant time. So the insert itself is constant time, which is fun, which is nice, a nice property of linked lists. Finding where to insert, not so much. And you might say, well, let's do what we did with a queue and store a reference to the end of the linked list also to handle that case. So we have the head of the list and the end, the last element of the list, references to them both, and then we don't have that issue. Well, now what if you have to insert into the exact middle of the linked list? It's still n over 2. Asymptotics don't care about constants. It's still O of n. You just can't get around that with a linked list. Not without a significant amount of complexity. Basically altering it into a different data structure is all you can do. So we can't do this with the data structures we know about already, but with a tree we can maintain sorted order in log n time. And I always like to think of like a top like a leaderboard. We have a global leaderboard for a game. We got millions of players around the world who are playing, and their scores are constantly updating in this list, in this leaderboard. When somebody updates their score, we don't want to O of n time to maintain that sorted order. We want to do that in log n time. We got a lot of players constantly playing the game, updating this thing. Let's maintain that thing in log n time. So for that, I don't talk about it in these slides, but we can also delete a node in log n time. So if somebody's score updates, delete it in log n time, add it back in log n time, and maintain that sorted order. So that's the advantage we get with a BST, is if you have dynamic data that you need to keep in sorted order, BST is going to be the best you can do. Getting these log n updates is the best you can do. We can't get down to constant time with this, unfortunately. Try as you might. We have constant time data structures, HashMap being one of them that we actually use this semester, but they're not going to maintain sorted order. And the details on that will be in 250. You have a whole semester of data structures. So when we inserted, or what did I use for the example? Find or insert? Find. So just to find a value, we're eliminating half the search space. This is the beauty of this, is we're eliminating half the search space every time we do a constant amount of work. So we check the root node, and we eliminate the entire right subtree when we move left. Then we're going to move right, and we eliminate the entire left subtree when we move right. We're effectively cutting the search space, the remaining search space, in half every time we do a constant amount of work where we're checking a single node. We can't do this with our other data structures. With I mean, this isn't 100% true. But with our other data structures, we'd have to check every node. With a linked list, we have to check every node. With a binary tree that's not a BST, that doesn't have this less than, greater than property, we'd have to check every single node. If we had an array list that's sorted, we don't have to check every single node. That's where binary search comes into play, which is effectively the same thing we're doing here. Binary search, you would check the middle index, eliminate half the search space, check the middle index, eliminate half the search space, and you could find an element in log n time. If you have a sorted array, that one you can do. If you have a sorted linked list, you can't do binary search on that because you have to follow get next, get next, get next. You still have to look at every single node. So this is something that we can get with a tree. We could only ever get with an array, but with an array, we couldn't insert and maintain that sorted order in faster than O of n time. So this is a nice property that we have. And notice that the height of this tree is 3. So we only got to check 3 nodes to get all the way to the bottom of the tree to find out if the value's in there. We don't have to check all 7, which, is kind of an improvement. Okay, 7, that's a little more than double the work, but, big deal. Not that great, right? But what happens when this scales? How does this scale? So what if instead of 7 nodes in our binary search tree, we had 1,000,000 nodes? We got a binary search tree with 1,000,000 nodes. I'm obviously not going to draw them all, but a binary search tree with 1,000,000 nodes. What's the height of that tree going to be? What's this height going to be? Where with our binary tree of size 7 nodes, we had a height of 3. When we have 1,000,000 total nodes, what's the height of this binary search tree going to be if it's balanced? If it's balanced. If you guessed 1,000, you're completely wrong. You're way off. If you guessed 500,000, it was roughly half before. So if you guessed 500,000, you're completely wrong. It's about 20. Now, this is the power of logs. Logarithm is an extremely advantageous function for us in computer science. It gives us so much efficiency. 1,000,000 nodes, take log base 2 of that, it's roughly 20. If you had 1,000,000,000 nodes, it's about 30. Trillion nodes is about 40. Every time you add 3 more zeros, you're getting another plus 10 only. Just plus 10 on your logarithm. This scales extremely well. So the log base of 7, which is about 8, the number of nodes in the tree is actually, if it's a power of 2 minus 1, we add 1 and then take the log base 2, that's going to be exactly our height. So 8 plus 1 is 8, and then the log base 2 of that is 3. So that's why our height's 3 here. Same thing here, 1,000,001, log base 2 of that, it's going to be about 20. It's actually a little less than 20 for 1,000,000 nodes. So you're finding a value in a tree with 1,000,000 nodes. It's going to take 20 checks, 20 nodes you have to go through. And this is exactly the math, how those 20 questions games, where you have the game where it says, think of anything. Think of anything. I'll ask you 20 yes or no questions and tell you what you're thinking of. This math is how that works. It can be coded to have 1,000,000 things of it in what's called a decision tree, where each node is a yes or no question, and you either move left or right, whether the answer is yes or no, and then eventually get down to one of the 1,000,000 leaves down here, which are going to be, if I'm programming that, it's going to be the 1,000,000 most common things that people think of when they play a game like that, and code quite a bit of stuff in there. And then build that decision tree based on a whole bunch of data that I pull from wherever, and then figure out which questions there will be to build this tree in a balanced way, and then have it ask you those questions and get to that node that you're thinking of. That's how those games work. It's not just magic, it's not mind reading, it's just math. Just math. 20 questions, 1,000,000 things. And then sometimes you'll have the games that it's like, okay, I couldn't get it in 20, but give me 5 more questions. Well, yeah, now it's got tens of millions of things that it could have coded. I think the trickiest, if I'm thinking of programming those things, the trickiest thing would be when somebody gives me a wrong answer. Sometimes, I'll be playing those games and I won't even know the answer. Like, is a refrigerator a carnivore? Yes or no? I don't know. Which I probably answered a question wrong before that to get a silly question like that. But anyway, that's how those work. If the tree is balanced. Why do I keep emphasizing that? Well, our implementation is crap. What if I insert my values in this order? Everything in this lecture was very carefully constructed and crafted to make sure the tree is going to be balanced. What if I insert my values in sorted order, though? So if I insert my values in sorted order, or reverse sorted order, I'm going to get something that's basically a linked list. I have O of n insert, I have O of n find, everything sucks. I just have a linked list with all my O of n operations. This is bad. If I have 1,000,000 elements, I have height 1,000,000 if I inserted them in sorted order. And our methods don't do anything to address this. We're just screwed from jump. So the BST we built in this class is not to be used for efficiency, which the only real reason to use a BST at all is for efficiency, so not to be used. So how do we fix this? I can do this in one slide, right? We're on the last slide. Well, no, I'm not going to fix this. So how do we maintain this balanced structure while we're inserting it? Because find just takes advantage of the balanced structure and the properties of BST. But how do we maintain the balanced structure of a tree when we're inserting and still insert in log n time? How do we remove nodes if we have how do we write a delete method? And with the same thing, how do we write a delete method? What if we have to like delete the root node and we have to do that in log n time? How do we even do that? And how should we actually handle duplicates? Should they be allowed or not, left or right? This one I don't think 250 is even really going to answer, but the rest of those questions and much more answered in CSE 250. This is last few slides were basically foreshadowing 250, advertising it or whatever. What you're going to see in 250. It'll look a lot like that runtime stuff we just talked about, but for an entire semester and with a whole bunch of data structures that you're going to learn about. And the short answer for the balance stuff, you're going to learn about something called self-balancing binary search trees. These are binary search trees which do exactly that. They maintain the balanced structure. They at least keep it close to balance on the asymptotic order of log n, so O of log of n. And what it would do is roughly when this 4 is added, it might wait till the 5, I forget exactly. But once this tree starts to get really imbalanced, what it'll do is a rotation. It'll rotate, so instead of 3 being the root, it's going to rotate 3 down, promote 2 to the new root, and then 4 will still be the right child of 2, and then everything else, as it gets more messed up, it'll rotate more often, but it'll actually change which node is the root and can have internal rotations. Like this 5 might rotate down and put 7 up here and pull 8 and 14 up. It'll do those rotations to maintain this sorted order and also the balanced structure in log of n time. It has to do that efficiently by manipulating the references. You'll learn about AVL trees and red-black trees are the 2 different implementations that handle that. And they're pretty fascinating. They're kind of, I don't know, the details, I always get bogged down on the details. It gets kind of boring at times. But the concept itself, I think, is pretty fascinating. And removing, same thing. If you remove a node, like if you remove the root, like I said, you pick either its left or right child to kind of pull up to be the new root. And then figure out which one of its children will replace it. And you recursively fix down the thing until you get to one of the leaves. Okay. That's trees. So as promised, let's take a look at programming task 5. What do you have to do about trees? We already talked about the quiz, so let's talk about the coding a little bit. And we should be able to do a little bit of, I don't even have IntelliJ open right now, but a little bit of debugger practice too. All right, so we're gonna test data structures too. This is a class you'll have to create, and then follow the structure of the other testing classes, and test a playlist class, which is going to have a constructor which takes a comparator. And when you're testing, you can use one of the 2 comparators that you created in the previous task in task 4. I'll give it one of those comparators, either sorting songs on Bayesian rating or on title, ignoring case. And then you have an add song method and a get song list. Get song list is going to be the big one that you're going to work on for most of the homework. For the constructor, the idea, I don't mean this to be like tricky or anything. The idea here, so I'll just come right out and say it, is that you create a BST. You can use the BST class that we just went over in lecture. You can just straight up use that BST. I'm not concerned about you implementing your own BST. Just use that BST class, just like we did the linked list class. Take the whole BST class Don't modify the BST class unless you have a good reason to and you want to for fun or whatever. But take that whole class, put it in your data structures package, and use that class. So in your playlist class, you should have, I don't know why this keeps coming. I don't want this to come up. In your playlist class, you'll have an instance variable of type BST of song. That's not meant to be a tricky part. I say that because last semester I had so many students just doing all kinds of different stuff that wasn't just creating an object. But you should just create an object of type BST, throw this comparator at it that you got in your constructor, and store that in an instance variable. Add song. Guess what BST has? An insert method. We just went over the whole thing and talked about how it worked and everything. I gave you the code for it. Add song is as simple as calling insert. Your BST can't be null because you're initializing it in your constructor. It only takes a comparator, and then its root is going to be null, but it does the null check. So add song is straight up BST.insert. You don't have to do anything with this one. The purpose of the homework, where you're getting your practice, where you're getting your educational value worth, is the get song list method. Actually, not this one exactly, but this one, get song list, that takes a binary tree node of songs. That's going to be the root of a binary tree, and your task is to do an in-order traversal on that tree and return all of the songs in that tree in a linked list in sorted order according to the comparator you got in the constructor. So you have to do an in-order traversal. We did an in-order traversal. You had all the code and everything for it, which just printed to the screen. You had another one that concatenated strings. For this one, you have to, is a little trickier, but same concept, is doing the in-order traversal, getting the return values of the recursive calls, which will be linked list nodes, the head of linked list nodes, and you have to combine these linked lists and the value at that node into one single linked list. And the trick here is that your first recursive call is going to return the head of a linked list of all the values on the left subtree. The right recursive call is going to return the head of a linked list for all the values of the right subtree. And then for the node you're visiting, you'll create a single node, which will, I guess, technically be the head of a linked list for that single node. And you have to combine all three of these linked lists into a single linked list. So manipulating your references in a way to make sure that you get those in the right order. That's the part that we're working on here. So the binary tree, doing a traversal, so making sure you're getting your recursion down. Or if you hate recursion so much, you can try to do this without recursion, but I don't recommend it unless you want the extra challenge. So getting that first kind of semi-forced recursion, navigating a binary tree, and getting more practice with linked lists, and in general, just getting practice with nodes and references, these node-based data structures. That's the idea of this homework. So don't get bogged down on adding songs in the constructor. Those are meant to be straightforward. What else do I want to say? Make sure you get this in your ratings.datastructures package. This is used for testing. Make sure you have it identical exactly. It's just the binary tree node from class, except the full thing. I never showed the getters and setters in lecture. There they are. They're just getters and setters. I don't think there's anything else I really have to highlight for this one. But traversing a binary tree and converting it to a linked list in sorted order. That's the core of this homework. So if you're struggling at anything that's not this get song list method, you're probably overcomplicating it. Post on Piazza, ask questions in office hours, and we'll get you to the point where you can get to the core of the homework. Unless testing. I mean, testing is a big part of every homework throughout this semester, so except tasks 2 and 3. So these might get you a little bit too. With the Bayesian ratings, Make sure you're remembering why we use Bayesian rating. I don't know why I will, and I will this semester too. I keep getting this question of my incorrect solution. Bayesian rating adds no ratings. Everyone gets tripped up on this. Make sure you have at least one test case where, or actually, this might be for test 4. I don't remember. But when you're testing Bayesian ratings comparators, oh no, because I removed the testing component for that. I might have got rid of the need for this. But if I didn't, when you're testing the Bayesian rating comparator, no, I think I got rid of the need for that. I think I said I don't even want to deal with that anymore. Didn't have much to do with the learning objectives of the course, so. But so many people were testing. When they had to test the Bayesian rating comparator, they didn't give it a test case that actually cared about Bayesian rating. So I had an incorrect solution where the Bayesian rating comparator was just comparing the average rating without doing any Bayesian stuff at all. So many students couldn't get a test case that made that one fail, which is a complete failure of the testing then, because the whole point of the Bayesian rating, using Bayesian rating instead of average rating, is to handle the things like I talk about in task 4, where you have one song that's been rated 10,000 times and has an average rating of 4.99, and another song that's been rated just one single time, but that single rating is 5.0. If we just use average rating, the 5.0 song is going to be rated higher than this 4.99, but hopefully we all agree that the 4.99 song is a better song. That's a song you're going to want to listen to, at least with all likelihood. Maybe the other song's a brand new song and just only one person got to it so far and rated it so far. But the probability is that the 4.99 song is a better song than the 5.0 song. So we use Bayesian average rating to make sure this 4.99 gets the credit it deserves, and the 5.0 is not ahead of the 4.99 with way, way more ratings than the 5.0. And so many students just wouldn't write a test case for that. So I'm pretty sure I avoided it, but if I didn't, just write a test case for that, man. What y'all doing? Make sure you write a test case to make sure the method is doing the reason why we wrote that method to begin with. Is pretty standard testing. Like, the fact that I had that confusion so much shows me that I gotta focus a bit more on testing in lectures. All right. How hard are 250 and 220? Hard. They're hard. I don't know if Gerlene's in chat, but she might be better to. I'm so far removed from that. I actually never took 220. It didn't exist when I was in college, so I don't know what that's like as a student. 250 is pretty tough, and I think just from talking to students, I think 220 is at least on the order of difficulty of 250, and you're expected to take them both at the same time. They're both harder than 116. I'll tell you that right now, right off the bat, for sure. How much harder? It's hard to say, and it depends how much. It's just like 116. Like 116, I don't think is. Some of you are gonna get mad at me. Just hear me out. 116 isn't that hard of a course if you know your 115 content inside and out. If you really crushed 115, it just all made complete sense to you and you know the hell out of that stuff. 116 isn't too bad. It's just a continuation of your education. That's the way it's designed to be, of course. What makes 116 so hard is a lot of students, some of you included, I'm sure, come into 116 with a somewhat fuzzy grasp on the 115 content. Like the very first homework, like the average is the accumulator pattern. The find best key, that's just finding min, or well, max, I guess. Those are things that you've did in 115, but some of you struggle with just the approach of those ones. Like, you're just lacking some 115 background, which is fine. You can get caught up and stuff, but it does make 116 feel a lot harder. if you're still understanding 115 concepts. So the same is true for 220, 250. 220, it's going to take what we've done with memory diagrams and just ramp it up. You're doing everything in C, which really cares about memory way more than Java does. So if you're fuzzy on the memory diagrams and you just squeak by the quizzes just barely, 220 is going to kick your ass, and it's going to feel hard. If you're crushing the memory diagrams, you're getting 4s in your feedback, and you know the hell out of how memory works in Java, 220 is not going to feel too bad. It's just going to feel like a continuation of your education, like it's supposed to be. 250, if you're struggling with linked lists, trees, and graphs in 116, 250 is going to kick your ass. If you're just barely squeaking by the data structures content in this course, it's going to be tough. But if you're crushing it, you know the hell out of, like, you watch today's lecture about trees and you're like, yeah, that makes sense. I got this. You do the same thing with graphs. You did the same thing with linked lists. 250's not going to feel too bad. But if you're fuzzy on any of that stuff, any of those gaps in your knowledge are going to absolutely crush you in 220, 250. Not to scare you at all, but it's going to, I do kind of mean to scare you because, like, I want to prep you for what's coming up ahead. And that is the whole reason why I have this grading structure that I do, is because any gap in your knowledge crushes you next semester. So I want to make sure you don't have gaps. This isn't perfect. Some of you can still get by, especially on the programming tasks. Some of you just have really hacky, crappy approaches where you get through an assignment without really understanding what the homework was designed to teach you. And that's going to catch up to you in 220, 250. But I guess my short answer is, if you study everything and you know what's going on this semester, 220, 250 aren't as bad as they will be if you try to cheese assignments and get through learning as little as possible. Like, I never understand it, but what so many students do is try to learn as little as possible, and they treat each assignment as an obstacle that they have to overcome, and they treat it like it's like that homework's deadline is the last day of their lives. Like, there's nothing that comes after that, and that's just a bad approach. Okay, I went way too long on that. Would you recommend taking 191 and 220 at the same time? I think you'd be fine with that. 191 isn't too bad. But 220 will take over your focus. Anyone who takes 191, like a lot of you are, taking 191 and 116 right now, 116 takes over your life, and 191 kind of gets put on the back burner. It'd be the same thing taking 191 with 220. Why am I always getting cannot find symbol class? I mean, you can come to office hours. Or post on PI. There are many other things you can do except that's not asking in chat. Looks like y'all are agreeing with me about 191. Alright, let's get a little debugger. I'll feel bad if I don't get to some debugger. We're past the halfway mark, by the way. Holy shit. And I want to do a memory diagram for our binary tree without the BST, because I'm not going to put BST on the quiz anyway, so it's not as helpful to go through that in the debugger. So now that we know the debugger and we're learning more about memory diagrams, I want to go a little bit more in depth here. Actually, I'm going to set this right here, right? 122. We don't need to click through all the constructor calls. But I'm going to set my breakpoint right here. Since we've only seen the debugger once, let's take it from the top. I'm going to set a breakpoint. What that's going to do is when I run my program, I'm going to run it in the debugger. I'm going to use the debug button to run my program. And what that does is runs the program just as normal. Normal run of the program. There's a lot going on behind the scenes, but to us it's a normal run of the program until it hits a breakpoint. Once the program hits a breakpoint, when it reaches this line, it's going to put the brakes on and just stop. It's going to completely stop dead in its tracks and show you everything that's going on in memory. And by in memory, I mean the same thing as we're seeing in our memory diagrams. Everything you're writing in your memory diagrams, it's going to show you. Sometimes it'll show you in a different format. It'll show, a few things a little bit different, like it's showing root.right and root.right.right, just to give you easy access to instance variables, for example. But root, I think the glasses mean that it's showing you extra stuff. Root is the only actual variable inside this stack frame. Notice that we don't have this in here because it's a static method. That wasn't something magical we did for our memory diagrams. That's actually what happens. So this is the same information in our memory diagram that we get shown in the debugger. So if you're trying to practice memory diagrams, run the debugger on a program and take a look at what's in memory. Ideally, this is what I would do if I were studying. I would write a program or just take any program out of the examples repo, draw a memory diagram, and then run the debugger step by step and see if it agrees with what I wrote. See if what actually happens is, in fact, what I have on my memory diagram. That's how I would study. Everybody asks for more example memory diagrams, more than what's in the slides. You can create infinite memory diagrams by running the debugger. So right now in this stack frame, this int example stack frame, so we have the name of the stack frame. We have the line that's currently executing. In this case, it's the line. So when you set a breakpoint, it stops before this line is executed. So line 100 is the line that's about to be executed. And we get all of the values on the stack at this time, which is just this root node. And then we can click this arrow. This arrow is effectively our dot operator in the debugger. This is going to follow the reference. It's going to say root stores a reference to a binary tree node that's at 767. And if you click this, it's going to show you the instance variables of the object being referred to by this reference. So that's going to go over to the heap and show you what's on the heap in this object. It has a value with the value 5. It has left with a reference 768, and right, which is a reference 769. And of course, the numbers of the references are going to be different because it's whatever you made up and it's whatever we just happened to get when we ran the program here. But we can check left is going to be a node with the value 2. Its left is the node with the value -3, and its left is null and its right is null. And we can take a look at the whole tree and see if this tree matches what we expect to have. So we have a root of 5 with a left of 2 and a right of 8. Its left has a left of -3 and a right of 4. The root's right has a left of 7 and a right of 14, and all the other references are null. So this is exactly the tree that we saw in the slides, and we can see that in the debugger that it has all the values that we expect in the places that we expect. Then we're going to call our pre-order traversal. Actually, I'm going to show some more debugger buttons just kind of as they come up naturally. I actually don't want to see the pre-order traversal. I want to see the in-order traversal. I have a few options here. I can set another breakpoint here and hit the resume button. The resume button is going to continue the program until it hits another breakpoint. So that would get me right to the in-order traversal breakpoint. Actually, let's do that. I'll go back and do it the other way also. That's going to skip over all of the other stuff and get me right to this line. Not skip over, but it's going to run through execute and then not freeze everything again until it hits my next breakpoint. And we have this other tab, the console, so we can still see what's being printed to the screen. So we see that the pre-order and post-order did execute. We got these printed to the screen. And then we stopped again when we got to this line. This button is going to rerun the debugger, so it's going to start back from the top. You notice that you can't go backwards with the debugger. We can only step forward with the debugger. So if you have to go back, you got to rerun the whole thing, get back to your breakpoints, and get back to where you were. So if I don't set the other breakpoint, the other way I want to do this is if the next line, I know it's going to create stack frames, and this is going to create stack frames on stack frames and go through a bunch of recursion. If I don't care about any of that, I'm going to click this step over button. That's going to skip the entire next line and not go into any stack frames that would be created in that line. And I'm going to skip this post-order traversal as well. And then now that I'm at the in-order traversal and the highlighted line, that means this is the line that's about to be executed. So this is the line that's about to be executed. I'm going to step into, which is going to go into any stack frames that are created. and I'm going to go into the in order traversal stack frame. Whenever it shows you this, it's asking you, hey, look, there's 2 stack frames that are created on this line. Which one do you want to go into? Usually if you just click step into again, it'll take you to the right one. So it'll take us into that in order traversal. But if you want to manually select, click on whatever highlighted one you want to go to. And we can go through our in order traversal. What I'm going to do here, just in the interest of time, I want to show you something cool, is I'm going to set another breakpoint at our base case, and I'm going to hit resume. So this is going to resume execution until it hits a base case. When it hits the base case for the first time, in fact, and I can see all the stack frames on the stack. So I have an in order traversal. Well, first my main method, which is just calling int example. Int example, where we were, is waiting for this line to finish executing. It called binary tree node, which is waiting for this line, the dot left, to execute. It has a reference to a node where node is value 5, and for some reason I made this one non-static, so I do have this as a binary tree node. And we can see that that reference has our whole tree. It's the root of the tree. It has all of our stuff there. And then out is the empty string, which called left, which made a left recursive call. It got a node with the value 2. Left and right are -3 and 4. It made another call, so we can see the stack here. And here the top stack frame is actually visually on the top instead of being upside down in our memory diagrams. This one got a node of -3 and made a left recursive call. And then finally this recursive call, this stack frame, got node of null. Which is just going to hit the base case and return. So we can see all the recursion. We can step through and see it making the right recursive calls. You can see exactly what's going on, which is exactly what happened in our memory diagram as well. But if you want more examples, run that debugger. All right, and that's the end of lecture. I'll take a quick break and hop on the office hour meeting. All right, have a good day, everyone.